Let's have a look at this problem here regarding food calories. Oh, I'm not going to read all of this. I'm going to leave it here on the screen. You can pause the video and read it. So let's go ahead now and solve this. And it says here in the first sentence, the food calorie equal to 4,186 joules. Now calorie is a unit of energy in the imperial system. This is a unit of energy using the imperial system or the English system. And in the metric system, for energy, we use the unit of a joule. This is the metric system. Basically, what's telling us here is an equality written in words. Well, let's have a look at our conversion sheets. And we're talking energy. And here's our conversion sheet. And we want energy, and it says here 1 joule, 10 to the 7 ergs, that's another unit of energy. Here's calories, we want this one here. 1 calorie is equal to 4.186 joules. 1 calorie, I'll write that down here. Calorie is equal to 4.186 joules. Well, that's a difference of 1,000 between the two. So what's happening here? Well, let's take another look. I have here some chocolate bars. This is actually my favorite word problem because I get to buy some chocolate bars, and when I finish all of this, I get a treat. So let's look at the food labels here on these chocolate bars. Let's choose one. I got several. Yeah, let's look at this one. It's a dark chocolate, Wendell. Look at the back here at the food label. And for energy, well, where is this chocolate bar from? Let's have a look at this. This chocolate bar comes from Poland. In Europe, they use strictly metric. So their energies will be in joules. But because they're exporting this to us, they need to also change it to calories, because that is the North American measurement for energy. It's not the metric measurement, it's just what the North Americans were using in the Old English system in calories. But it's also written here in joules. As far as energy goes, this one has 2,067 kilojoules per 100 grams, or 495 kilocalories. Let's write that down. I'm going to just turn my page over. 2,067 kilojoules and 495 kilocalories. Let's do a division between the two. Let's see what we get. And this is just a FYI. 2067 and divide that by 495. We have a number. And the kilos and the kilos, that represents 1,000. The two cancel out, so I have joules to calories. And that answer is 4.1757. We'll say 4.178 joules per 1 calorie. And that's from Poland. And let's have a look at another one. Here's another chocolate bar. And this one comes from, let's see, what's here somewhere. Imported from Germany. And let's see how they report their energy in this chocolate bar. And it says 2319 kilojoules to 557 kilocalories. And what's important to us right now is this term here, kilocalories. But let's do the math here, just the same, 2319 kilojoules to 557 kilocalories. and the case will cancel out. That comes to, whoops, 4.16, we'll go 3 joules per calorie. And that's similar to our conversions. 1 calorie is 4.186. This is due to rounding. The little differences we see here is due to rounding. So that brings us back to here. 1 food calorie, 4,186. Well, when these are reported, they're reported in kilocalories. I showed you earlier, in kilocalories, thousands of calories. But let's look at our system here in North America, because we don't work in joules or kilocalories. Here is another chocolate bar, and this one has the food label strictly in the Canadian system, the American system. And it says here for energy we use calories, and it has 170 calories written here. Oh my God, that's low. 170 calories. I'll have you note, when this is written, it has here a capital C. So what does this capital C mean? Well, now that we have all the information, I just need to move my chocolate bars aside. For our conversions, 1 calorie with a little c is equal to 4.186 joules. But in the Europe, they report these in kilocalories. In kilocalories. So 1 kilocalorie is equal to 4,186 joules. That K represents 1,000, so multiply that by 1,000. And this multiplication of 1,000, or a kilocalorie, has the name of a food calorie. 1 food calorie is equal to 4,186 joules. So we multiplied it by 1,000. That is known as 1 calorie with a capital C, calorie. In North America, this is how it's written. Instead of using kilocalories, they still use the word calorie, but they put in a capital C versus a little c. And this capital C right here, this represents 1 food calorie. Now let's still go on with the word problem itself now that we've understood what is meant here by food calories. And when you go to the store and you look at the labels, remember this, have a look at the labels, and you will see the capital C. And that represents 1,000 calories. This is actually 170,000 little calories. Or you can write down as 170 kilocalories. It's all wrapped up in this capital C, known as a food calorie. So let's go on with the rest of the word problem now that we have this understood. It says here, if a 65 kilogram hiker eats one of these bars, a bar that contains 140 food calories, how high a mountain must he climb to work off the calories? In other words, how much exercise must he do with respect to the height of a mountain in order to work off the amount of calories which he has absorbed from this bar. And now we need to look at this a little closer. Here's the individual. And he is going to climb a mountain. And we're not talking a super steep mountain like this. He's not a mountain climber in that regard. He's just going to take a stroll on a gentle slope going up a mountain. And here will be the x-axis. And he's going at some angles, going on a slope. And as you know, as you start climbing up, you start walking on this right here. Okay, working on on an incline, you're going to work off some energy. And what we're being asked to do is to find how high must he go, a little at a step at a time, to reach in order to burn off 140 food calories. You need to calculate this height. And let's look at this another way. Going across, let's say he's going upstairs. Going up a set of stairs. And here he is here, or her. We'll have to put a step on, 1 foot on the stair. And he lifts himself up, or herself up. And he lifts himself up to the next step. And up to the next step. And up to the next step. What the individual is doing with their muscles is lifting up their body. And their body has weight. And weight, and I like to write weight like this with the force of weight, pulls down towards the center of the earth. So with every step he's going up, the force he needs to apply is that it must be equal to his own weight in order to get to the next step. And to the next step, he needs to apply a force of equal to his weight to lift up. And lift up again, equal to his weight, and again, and again. And each time he lifts up, he travels that little distance. And he travels this little distance again, and this little distance. So he's doing work, is what he's doing. Work is equal to force times the distance traveled. In our case, the force that he needs to apply with his legs has to equal the force of his weight. So his force is going upwards, but that's equal to his weight in order for him to lift up. And the distance being traveled is the height of that little step. Not much different in here, except it's on an incline. And in the end, we want to know what this final height needs to be. When you're in order to climb all these steps or go up all this distance, we're looking for the final height. And that's distance right here. Okay, we can represent that with the letter S. And if we look at this, his weight is equal to mg. And this force right here, this could be substituted with force W. Force of his weight times the height that needs to be traveled. Call it S. Or we can represent this with the right-hand side. So the work being done is equal to mg, just representing his weight with the right-hand side, times the height that he needs to travel every little step. Well, we're looking for this one here at the very end. So we'll represent that with the letter H for the final distance needs to travel. This is both distance, height, that's equal to distance. All right, now that we have an idea of what the question is asking us, let's go back and solve. So we're given some information regarding the chocolate bar or the fruit bar, and how much energy is in this fruit bar that he needs to, the individual needs to work. And let's do some conversions. 140. This is food calories, capital C. And we need to change this into joules, because in physics, we're going to use strictly metric, so we need joules. Doing this conversion, 140 food calories into joules, 4186 joules per 1 food calorie, capital letter C. Therefore, the food calories cancel out. What we have left is 140 times 4186, and the unit is joules. And that's the amount of energy that is being consumed when he eats this bar. In effect, now this climbing the mountain, now he needs to burn off all of this energy. This will be his exercise. How much exercise must he do to burn off this amount of energy? And we had our equation for work. We just did that earlier. Work is equal to a force times the distance traveled. And we changed this earlier for it to represent the force of weight. It's equal to mg times the distance traveled. And s can be changed to another character, the alphabet, and we'll just make this work is equal to mg, and we'll call that h for the distance traveled, because he's going up, and we're going to just represent that distance traveled here, vertical distance, as h. There's also another equation here. Mentioned here that all the food energy goes into increasing gravitational potential energy. Gravitational potential energy. Well, let's have a look at our equation. Here's our equation. For gravitational potential energy is equal to mgh. So we could have taken another approach here and simply gone to this equation right here. Potential energy is equal to mgh. And you'll notice you arrive at the same answer. Question is, how much potential energy does he have? So that's why I used the term work, because we needed to derive this from the energy here. So the work that has to be done is this much. Now we just need to calculate h. Writing down a list of what is given in the word problem. The work that needs to be done is that value in terms of joules. The mass of the individual, because we need mass, is given to us as 65 kilograms. The work the force that needs to be applied by the legs is equal to his weight. And I talked about this earlier, and that's equal to mg, and we want to find the height. So let's put in values now into our work equation. The amount of energy that needs to be expended is the amount of the energy within the bar itself, and that's equal to this, 140 times 4186 joules is equal to 65 kilos, and g is 9.8 meters per second squared. I guess we can put that here in our list. It's understood. And when we're dealing with energy, g is always positive. In energy, g is always positive. And lastly, we want to find the height, the total height that the individual needs to climb. All that's left now is a little bit of mathematics. So everything here is multiplied. We want to isolate h. We need to divide both sides by these two terms. Doing so, 140 times 4186, and this is a joule, divided by 65 kilograms times 9.8 meters per second squared is equal to the height that we are looking for. Now, looking at the units, this term joule, well, within the term joule, by definition, this is a Newton meter. Joule can be broken up or separated into its base components of Newton meters. And here at the denominator, we have kilogram meters per second squared. Now, this combination of units, kilogram meters per second squared, by definition, is also a Newton. And the Newton in the denominator and Newton in the numerator cancel out, leaving us with just the unit of meter. And that's a good thing, because distance has units of meters. Therefore, solving all of this, h is equal to 920, and the unit that's left over is meters. So he needs to climb on a slight angle all the way up to a height of 920 meters in order to work off all of the energy from the bar, from the cereal bar. As far as part B goes, here is a part B here. I will leave that in the postings.